ask us. All right, so it's 6 past 2, and we can start talking about this week's lecture. So this week is a continuation to last week. Last week we started aiming for finding the bending capacity for steel sections, right? And where we stopped at, I think where we stopped at is finding the MS, which was the section capacity for a beam. MS, it's a section capacity. This value can be relied on or used if the beam was fully restrained. So, and we talked about how to determine that. Now, the example you did, I know we didn't have effectively a workshop last week because we had the test. During the walked example, we showed you how to find mainly MS. So if you all remember, MS was equal to Z effective multiplied by Fy. Fy is just the strength of the steel, which you're going to see from table, whether 300 or 340. We're going to use the table from the supplier, which is the one steel figures. ZE, it is what we talked about last week. All right, I just want to make this really clear. Now, up to now, part 1, we showed you how to find the section capacity, the section bending capacity. What does it mean? The word section means we're assuming the beam will not twist or buckle by like a torsion effect. We're going to see that clearly later on. So if the section was somehow checked to not fail in terms of lateral buckling, then we can rely on MS, and we need to find MS and make sure it's more than the action. We need to make sure it's more than the action, and that means design is done in terms of bending capacity. But what the walked example we did, it's all about ZE. If you remember, ZE can be calculated by 3 different formulas, depends on whether the section is compact or non-compact or cylinder. Okay, we have checks to do with cylinderness factors. You go through these checks, you're gonna be able to determine whether the section is compact, C, non-compact, NC, or cylinder, S. By determining which one is your section at, you will be able to use the relevant relationship, and that will give you Mr. ZE, job done. Then you multiply it by Fy, and we're done. Then you need to treat it by a safety factor Y, then compare it with M star. So I just want you to know where we stopped at. And I know we didn't do a comprehensive example yet because the story is not done. So one thing, sorry, while this formula was sitting there, I just want you to from now understand that ZE, yes, we taught you how to manually find it. However, you're going to see today, ZE is also available by the One Steel book that we're going to let you use. There's One Steel tables, where that tables give us sectional properties for the usually used cross sections like PFC, universal beam, a universal column. You know, we introduced you and people introduced you to those tables. Inside those tables, for each section, they actually gave you this. So someone's going to say, does that mean we don't need to calculate it? We don't need to study it? It's up to the question. Sometimes we may ask you to find it and show us you know how to do it, maybe in test 2. Sometimes because we have other things to let you work on, so you don't need to. So if the question specifically said find ZE from first principles or calculate ZE, then go ahead. If nothing was said about ZE, then you can just quickly take it from the table, because most likely the problem going to be with the bending with the member capacity, not the section capacity. So I said this from the start, and we're going to repeat it, but just understand. If you have any questions, let me know. If you don't know what I'm talking about, let me know. As we go through the lecture, always come in and ask if you have any questions about what I'm saying there. So yeah, that was just a quick briefing about what was done. We're still working with the same resources we talked about last week. Now, this image here is really going to tell you the difference between MS and MB. Okay, so if the beam, you can see here, if you focus, there is a load on the beam, right? Now, if the beam was very short, usually that means if the beam was actually very short, usually, and it was kind of restrained with some mechanisms, then the beam can take load all the way up to its sectional capacity. And usually this is achievable by short beams or long beams when are very well restrained at the top or the compressed side. So when I say top, I mean the compressed side because this is simply supported. So, however, if the span was like clearly long without restraining mechanisms, like maybe there is a rafter sitting on top of it or any other type of engagement at the top, then what's going to happen to it? It will tend to twist, right? It will tend to twist, and that's what they call it, the lateral torsional buckling. And then this means you have to go and calculate MB, which is smaller. Typically, it will give you smaller capacity than MS, and you're going to see MB is equal to alpha M, alpha S, multiple, the product of alpha M, alpha S multiplied by MS. Okay, so basically MB is equal to alpha M, alpha S, and MS is basically the one we've talked about last week. And I said to you, sometimes you can't quickly calculate it by taking ZE from the table, and sometimes you may need to know how to work out ZE from first principles and the basics we had in the standard. So this is the story behind lateral buckling and the kind of failure. I talked about this as the fifth case we had last week, but now today we're going to focus on how to find its capacity. This is just some images that you can understand how the twisting failure or the flexural torsion buckling can happen. There's a quick, I've just made it ready. Quick, I can send you the link for that. This is a very good, I will share it with you later on by, if you want to have a look. It's very clear video, which about conducting tests on beams. It's just simply a point load on this one here is a short beam. And if you can see from the video, I just started it now, they're actually applying the load. Now, what you can see, the main thing I want you to see for now, it is you can see it's actually flexing without being twisted. So this is the yield failure. This is where we have pushed the beam to its MS sectional capacity because they managed to actually restrain it. And the beam is quite short. The span is very small. So there's going to be no chance for the beam to actually twist left and right. So purely here, the failure is due to the sectional yielding failure. That's where I would, when I want to design the moment capacity, I would go and rely on MS, one we taught you last week. Now, if the beam was a bit longer, I think there's a good, here we go. I will share with you this video if you want to see it all. You see this one here, this was a longer beam. And when they tested it, see what's happening to it. It's kind of maybe this one, they say they're applying the load. And what's happening to the beam? It's getting laterally buckled. So it's just twisting. And this is the failure you talk about. That's why we're going to have a reduced capacity. We cannot rely on MS. We have to use MB now, which can get things factored down most likely for MS. The other, maybe I again suggest, we're going to put this on the chat link. There's also some good experiments they're showing you here how the twisting may happen. So, which depends on whether compact or not compact. At the end here, I've seen it quickly. You've got, this is a compact beam. You see this guy here is kind of a universal column. And while they're adding more and more load to it, it's not actually laterally twisting because it's compact. And the formula, which we showed you last week, you remember that left-hand right, left-hand side, sorry, right-hand side equation. For this side, it's proving to be okay. but the other one, it's not. So I'm going to add this later on this video to the link and give it some time. What's this? Let me stop it now. We're done. Yeah, so sorry, let me just close this thing here. Yeah, so that was really explaining these images, showing you that some sections depends on their properties. They may got capacity to resist buckling, which is fine, but some sections may not. And we had that left-hand side, right-hand side formula to tell us whether the section or the beam is actually fully restrained or not. If fully restrained, that means MS will be the gauge. If not, then we have to go and calculate MB. And MB is the story of our today's lecture. This is that left-hand side, right-hand side lecture I was talking about here. So this is the formula I was talking about. If we validated this formula and proved it's working, then it means that the section is fully restrained. If not, then it means the section is not fully restrained. Remember, this formula is sitting in your standard, so you know how to find it. And this one here, it's only applicable for I sections, like, for example, universal beam, universal column, but not a channel. We have to use a different formulas, okay? Or maybe welded beam, welded columns, I sections. You can use this relationship, and we used this last week. We showed it. We showed you how to use this relationship to answer different engineering problems. For example, in one of the questions we asked you, what was the maximum spacing between the roof rafters? If we have roof rafters sitting on top of the beam, what is the maximum spacing we need to put them at in order to get this validated and have the section limited by its sectional capacity, so fully restrained, in order to make it fully restrained. And then, so in such questions, our approach will be about using this relationship, but it's going to be about finding this L, which is going to be the maximum spacing of the restraint mechanisms. So again, this is the relationship which we use to tell us whether the beam is fully restrained, then MS is the guide, or not fully restrained, then we have to go and find out B. This is just a repeated image from last week's lecture, and it's showing you how the restraints can be used. These kind of structures, you see them in bridges or inside steel-formed bridges. These kind of details, it's in residential concrete apartments where we are able to make that arrangement of restraining the beam at its compressed side. Don't always think it's always at the top. We're talking here because the problem with buckling is the compressed side. Even that video I showed you, it was twisting from the top. So the upper side of the beam was actually leaning to left or right. And why it's happening at the upper side? Because it's the section which is under compression. Okay, the tension side does not buckle. As you know, tension, it's only going to fail at yield at the section capacity. All right, so again, this is just a reminder about the MS relationship. That's all the aim from this. We have nothing to really talk about it again. And last week we had one example during the lecture showing you how to find ZE by using the cylinderness factors we talked to you about. All right. Today you're going to see, when we start working with the one steel tables, you're going to see the tables actually show us ZE for X, ZEX, ZEY. They show it to us for each standard section. And yes, maybe if the question not asking you intentionally to find it, then yeah, you can go ahead and take it straight away. Okay. Now, someone gonna say, so what's the point of learning the basics? Because you're definitely gonna be involved in designing customized sections which are not in the standard tables. Like, it's not a standard section which is used sometimes, especially in the mining industry, or even some of those special featured structures. You may have non-standard shape. That means you have to use the principles you've been taught to find the correct ZE and then get things moving. Right, now this is what we kind of have in you this week. which is MB. So if your section is partially restrained, not fully restrained, we have to go and find the member capacity. They call this MB, they call it member capacity. MS, they call it the section capacity. Member capacity, as I said, it's very sensitive to buckling, to the lateral buckling, and that's where we're going to have it treated by these two guys, alpha M and alpha S. Just to let you know here, one of them going to be always reducing the capacity. This is the cylinderness capacity, which is always going to be most likely reducing the, it's going to be less than 1, which reduces the capacity. Now, interestingly, MB, sometimes it can beef up the capacity because alpha M, as we're gonna say to you later on the slides, it is to do with the shape of the bending moment. Depends on the shape. Sometimes the bending moment diagrams, they actually gonna help the beam to restrain itself. We're gonna talk about this later. So sometimes what I'm trying to say, sometimes alpha M actually is more than 1, which is good, which is helping us in controlling. Now, by the way, alpha S sometimes can cut down the capacity MS by half or by 60%. So imagine you've got 100 kilonewton capacity from MS. By the time you calculate alpha S, it may be 0.4. So 60% is gone. But fortunately, we got alpha M sometimes. If the bending moment diagram is actually got some hogging and like positive and negative in it, it will help to buckle itself, and then we may have 1.5 or 1.8 factor, so it helps in the design. So these kind of factors, they typically need to be carefully considered and calculated to come up with the most economic effective section in terms of finding MB. Now the slides here, first thing we're talking about MB, as I said to you, it's a moment modification factor that depends on the shape of the bending moment diagram. As I said to you, and most likely it will help us. What does it mean help us? It's more than 1. So it beefs up MB to us, or beefs up MS. Right? You can see, I think there's a small thing missing in this formula. You have to make sure it is not more than MS. It's in the standards. I'm sure all of you are going to use the standards to get these formulas. You have to make sure that whatever we have here, it does not go beyond the section capacity, because it does not make sense. You have the bending capacity more than the member capacity more than the section capacity. It's not possible. All right, now you're going to carefully use these formulas and use them. Alpha S here, it is, as we said, simply it's called the cylinderness reduction factor. It depends on how high is the section, how skinny it is. Usually a member like this is going to be more sensitive to buckling than a section, a shorter one with a very thick flanges and whips. So usually if you've got skinny flanges and whips and tall sections like that, they are non-compact or cylinder sections. They're going to actually be more sensitive to that lateral buckling more than a short section with very thick flanges, and so this guy will win and give you better capacity. And its alpha S can be actually closer to 1, but this one, its alpha S will be far away from 1. Like 0.6, 0.45. Okay, just so you sense the numbers there. Right, so yeah, this is again the formula we had. As we said, after you go and calculate your these guys correctly, we're going to talk about them a little bit more later on, just to make sure things are clear. So we know how to find MS, we know how to find alpha S, we will know how to find alpha M as well. And this is just a capacity factor which we use from special tables. Typically for designing steel for bending, they're going to be 0.9. So whenever we do calculations, we always have to have safety factors due to mistakes, whether on site or during design. So we're going to factor things 10% down. And that means you ended up finding the actual member capacity. We call it now capacity when we multiply it by the capacity factor phi. Okay. Now we're talking about a little bit details, and I think I will try to go through them with some points, but carefully try to think about each as you go through the example. Next, we have one example. Slowly, we're going to go through it. And so alpha M here, as I said, it is the bending shape factor. And one thing I want to tell you here, sometimes the standard will allow you to take it only one. Right now, see, you see the standard. If we're going to open, it's going to ask us. It can be taken as one, or it needs to be calculated from tables, or it needs to be calculated by a formula. All right. Now, taking it as one straight away, it means that you will never get any advantage from alpha M, which means your design will not be economic. And your section is going to be bigger than other engineers who actually have spent time to calculate it more accurately. Option 2 here, we need to spend a little bit more time and use table to go and find it, which we're going to practice a little bit together now, next in the coming slides. There is a third option. So these are options, how to calculate alpha M. There are actually 4 options, okay? Now, what we're going to practice in this course, we're going to practice number 2 and 3. In our examples, we're going to practice number 2 and 3. Now, in a test or exam, we will either give it to you, like what we did with our wind loads. We're giving you a lot of things, and you know how things are. We're either going to give it to you, or we're going to intentionally ask you to calculate it because it's part of the process we want to assess you in doing. So, however, I don't think it's, if we're going to give it to you alpha M is equal to 1, then that's it. We've given it to you, alpha M is equal to 1. In a real design practice, by the standard, you are able to use whichever method. They all should give you the correct, safe, conservative design. But this one here, it's very, very conservative. It's too conservative, and it may not be economic. You cannot do this in real practice, unless if you're designing one beam, and which does not really matter for the building. Like very few beams. All right, now, so that was the idea behind alpha M. And all right, so part of alpha M, I think if you go through the definitions here, which you're going to practice with the examples, it will ask you to find within the tables, especially, we're going to look at it together now, within the tables formulas, they are in function of finding a property called beta M. Beta M, again, as defined in the standards, is the ratio between minimum to maximum bending that beam is experiencing. So we have, this is one segment of the beam, right? So it's restrained here and restrained here. And we need to know what type of bending the beam is experiencing. You just need to put the minimum value, which is 30, over the maximum value, which is 100 in this case. The only attention you need to put here is you need to put the right sign, whether negative or positive, right? Now, someone can ask, when do I put negative? When do I put positive? If you need to use imagination here. If the beam, due to the bending action, will be curved by single curvature, then that means you have to put the beta M negative. You have to use negative single curvature, right? And how this is, again, if the moment got the same direction. But remember here, someone will say, no, it's not. This is clockwise and this is anti-clockwise. Sorry, this is clockwise and this is anti-clockwise. Well, yeah, because here I'm looking from the right and here I'm looking from the left. So the best way really to imagine this, if you hold a book or a piece of paper like this one here, yeah, and let's try to follow what's happening with this case up here. I'm going to twist my hand with the same way. See what's happening to the book. It's with a single curvature. So that's really what does it mean. All right. Now, if we go to the other case here, where one side was positive and the other side is negative, that means one side going to turn. So we're going to have double curvature. Yeah, it depends on how we apply the load. So going back to the single curvature, you can see we hurting the beam, we stressing the beam, or we flexing the beam more than what we're doing here. If we're going to have that negative and positive, eventually the flexing action on the beam gonna be less, with less effect compared to if it's single curvature. That's why with single curvature, typically it's negative. So it's gonna have some kind of penalty, yeah? Like it's gonna reduce the capacity even more. So, you know, again, what we're talking about here, I just want to keep you focused. We're trying to calculate this guy. Within the process of calculating this guy, we need to go and determine beta m. While we find beta m, which simply comes from dividing minimum bending over maximum bending within the beam, you have to just imagine and determine whether it's negative and positive. And you're going to see this as well from different examples, right? So before we leave the alpha m, there are really examples here. Before I talk about this one, let me do this is a bit much more easier. So this is just a cut from the tables you're going to use in the standards. And let's say here in this example, we have a single beam, simply supported beam, carrying a load as shown, and will end up giving us this bending, right? So in order for me to use the table, I need to determine which shape within this column of the table is actually applicable for our case. Someone gonna look at it and say none of these shapes are actually similar to this. However, if we assume these ends are 0, right, we will end up having this shape. So effectively, I will be able to use this formula. Remember now, I know the cut here didn't show you. This is actually, these formulas will give you the alpha m, by the way. Because if you look at your standard, you're going to see the top of this column, the top of this table is alpha m. So these tables are going to help us to determine alpha m. And as you can see here, within there, we got beta m. That's why we have to use beta m, which I was talking about. All right. So effectively here, as I said to you, by using our engineering inspection there, we will be adopting this case, right? Why? Because I know I will be able to do something about this negative bending here, okay, and get it to the shape I have. So what we're gonna do, we're gonna carefully think about beta m. Now, beta m, remember it was minimum and maximum. In this case, our minimum is 0 because we don't have bending at the end. So our minimum will be actually 0, and you end up with beta equal to 0. So you're gonna actually take away all this end from your formula, and your alpha m will be effectively 1.13. Just showing you how. And see, so this is helping our beam by 13%. It's gonna beef our MS by 13%, but remember, we're still gonna multiply it by alpha s, which will take things down effectively. So you just need to carefully select which case you have here. As I said, this shape is applicable to be here because in our case here, we don't have these ends, and you can assume it will actually go to 0, and you work it out from there. Right, let's see another example here. So in this case, is someone able to tell me which case you're going to take there? Should be really straightforward here. So which row is it? 1, 2, 3, 4, 5. Which one? Just say it or write it. Correct. Same story. Yeah, that was right. Number 5, same story. We have 0 bendings at the end. So that means we still are able to use this relationship because the relationship will work out the reduction in the negative bending. Okay. So by the way, this one still works if you're going to get it right in the way where you're going to put the location of the force in the middle. So if we're going to have 2 ways, and both of them, they're going to give you the same value. All right, just to let you know, this one will work as well. You just need to put the correct value. Remember here we got the distance. If you put the distance half of the span, it will give you the same factor as we're gonna calculate it from here. But we will go through this during the examples. Now let me quickly go to the first one, which is part of what you're gonna practice in the workshop as well. So this is again the beam we start working on last 2 weeks, and then we stopped to talk about the wind loads. Then we're going to come back to finalize this design. Now, as per at the end of our calculations, or from statics, from SD1, you would need to plot the bending moment diagram, which looks something like this, right? So this is the bending moment diagram. We got positive here, then we got negative there, then we're going to get it to 0 at the end. So yeah, and the solution we showed you, but can someone tell me, I know here I'm putting 2 arrows, but I think it's going to make clear sense to you again. So basically the backspan, or from A to B, when I want to find my alpha M, I should be chasing this case here, because see, it's same shape. Okay. If I want to check this side of the beam, the shape is here. Now, just one thing, someone will say here the curve is up, and here it doesn't matter, because in our practice as a practicing engineers, we like to show the negative to the top, but usually textbooks show the negative to lower, because they know everything under the 0 goes negative. But just to let you know, in practice, usually the negative is at the top for reasons we will talk about maybe at different times. Okay, if you need to know why, ask me. So the shape is same, and basically just need to follow the correct trend there. Right, so that was the story behind alpha M. Okay, now sometimes we may give you in a test alpha S and ask you for alpha M, or vice versa. We may give you alpha S. We may give you alpha M and ask you to find alpha S. Alpha S here, it's typically going to be cutting down MS, because usually it's less than 1 significantly. So how to find it? I think here there is one clear method to do so, and it's one of the longest equations you're going to see. So we know this takes time if we need you to find it, and it's just this one equation. It's got several ingredients to find. Some of them you just need to find from analysis. It's like the service actions, yeah, like sectional capacity. This is MS, which we already going to calculate. And in this case, obviously, we will not ask you to go and find ZE. We will just ask you to work it out by, we will say nothing. And definitely when you're going to find MS, you're just going to go multiply ZE from the table by what? By FY. And you're going to find it out, because we said this many times, MS is FY by ZE. And ZE, as we said, you can get it from a table, so it's not a big deal there. The other properties, this guy here needs its own relationship, unfortunately. This is the buckling moment capacity. It is to do, again, to measure the buckling capacity, which is the story behind the whole topic this week. The video I showed you, it's all about the buckling and the twisting. This property will give us that indication, and it's in function of the length. See here, the length, the effective length, the span of that segment, because it depends on how frequently we restrained it. All right. Now, just make a good try to clearly distinguish between the span of the beam, like from a column to a column, and how frequently we're restraining it. Pay attention to this, because here, this is actually the restraining. This LE, it is how frequently, it's not the full span. Okay, and so in some of our examples, we're going to tell you there is no restraining in the middle. Some of them we're going to tell you there are. So always, as you go through the solution, don't mix between the two. So LE here is the effective length of the segment, subsegment section, which is by its own in function of another 3-4 properties, which they have their own tables. Really, these things are, again, simpler than the wind load and those scenarios and cases that you've been going through, but just give it the slow time of studying to get on top of it. Now, I will leave this really, I think, so for at this point, alpha S is the second guy we need to find in the relationship. And simply it comes from these two main relationships or formulas. And the ingredients inside them will be coming from tables, which I will leave it to the worked examples to show you that slowly. So, that's what we're doing here, showing it to you step by step. I strongly suggest you, as you go first time through the examples, open the standard and the lecture notes to get it in the best way. Then if you are on top of the terminologies and topics, then just you can simply work with the standard if you know how to get everything. So you can see those, simply these slides are showing you the backgrounds behind each factor here, and then they're going to multiply it by the actual L, and you have to calculate them correctly because you're going to end up with more economical design, better design. If people keep ignoring these factors and they say 1, 1, 1, sometimes you may be over designing or under designing. So you need to get them right, which depends on the restraining mechanisms. Like for example, the last factor here, which is called KL, it depends where are we connecting the rafter to the beam. Are we connecting the rafter to the beam at the top by a cleat and then the rafter is like the purlin? Or are we connecting it with a cleat here with 2 bolts? So see, it makes difference. The way we're connecting things, it makes difference. And again, you're going to experience this, and we're going to talk to you about these kind of definitions, which is well defined in your standard. So yeah, I just want to close up because I just want to keep good time for the example to run through all these properties carefully. That was just the last factor, KR, in this LE business, and you will know about it as well. It is to do with whether the buckling was due to rotation or a twisting. There's a difference between them, which we're going to look at it. Now, that's all about the bending. So that's all really we need to tell you about finding the member capacity, right? Alpha M, alpha S, and Mr. MS. And there's also a phi here, just to make it. All right, that's what you really need to get on top of. And you're going to have 3-4 examples over this week and next week, because next week there's no teaching next week, by the way. I mean, next academic week, which is week 7 after the coming week, you will have a guest speaker, and I think you will also be practicing careful examples about this. Any questions about bending quickly, like anything that you looked at and not making sense? I'm happy to discuss them. If not, I can go to another design check for strength. And so at this point, we're done with designing the bending capacity of a section due to for bending. But we're not done yet for strength, because the beam may still fail due to shear. Yeah. And this guy, we have to check this. So what we checked so far, we made sure our M, whether B or S, is actually more than M star. That's what we've been talking about from week 5 up to this second. Now we're gonna put this aside, and we're gonna put all this aside. Whether it works, which should work at the end of the day, we're gonna go check the shear capacity. Which the good thing is really straightforward. There is not a lot of tables to use. Very easy. Usually, this is going to be like a good credit, and if it was coming in a test. So it's easy to learn, easy to apply, easy to check. Not really. There is no issues there. So let's see. Again, just quickly taking you through some facts. When a beam resists shear, it will be mostly resisted by the web. That's one thing you need to know. So we call these guys flanges, top and bottom flanges, top flange, bottom flange, and this guy I hatched, it is the web. And if we do stress distribution on the cross section, something we can get from mechanics of solids. We will, you remember in mechanics of solids when we said to you there are shear which goes into the page and shear goes across the page. If we go and plot the stresses going across the page, you're going to see most of the stresses going to be applied. You can see here, most of it. It's only this little part and this one, it's going to be resisted by the flange. So we just ignore it. But this other area here is heavily resisted by the web, by the DP depth. So we just want you to know from here that usually the critical element in our section is Mr. Web, and web will be resisting effectively the shear. Now these guys, remember, the flanges are busy with resisting what? Bending, because most of the bending really help us with, and all the checks, ZE and all that stories behind it was giving the axial stress due to bending, whether tension or compression on the flanges. So, all right, so tell me how to design for shear, which is all about how to find the V. All right, depends on, again, whether your failure gonna be due to yield or gonna be due to buckling. So same thing, if you have a section which is really tall and skinny, this will be sensitive. The web itself may actually buckle like this before it's actually get yielded, right? Then if you're going to do some checks by this relationship, just simply need to apply this check. If you find your check here or this relationship is giving you a value less than 82, then the beam is kind of compact and it's going to fail by yielding, and it's going to give you really high capacity. Then what they're saying to you, go and find your VV, right? Your shear, I don't want to say capacity because the word capacity should be used when you multiply it by 5. The yield ability to resist shear gonna be up to this formula. So remember, this 0.6 is already safety. Just to let you know, shear failure usually is very critical and sudden and brittle. Unlike the bending failure gonna give us some warning because the beam gonna deflect and people can see the danger and do something about it. But shear, if we shear something, it's just gonna fail in one go. There is no warning. So that's why usually the standards apply good safety factors. You can see we're gonna kill it down by 40%. And then simply what we're doing, we're multiplying the area of the web by the steel yield, which is 300 or 320, whatever the web strength is. Very easy, nothing really complicated. If this formula gave us a figure of more than 82, then we're going to know the web will not actually yield, it will buckle. Then we have to use this relationship. By the way, these two relationships are sitting in our standards because usually the standards which involve some safety measures, the standard's going to put it for us. If there are relationships we use from mechanics of solids, then you have to work it out. Unfortunately, with this subject, most of the formulas we're using, they are sitting in the standards, so you don't need to really memorize. Unlike in concrete design, some of the processes you have to call concepts from mechanics of solids or other engineering principles. Okay, so really that's the story behind shear. You just need to work out this guy, full stop. And this guy will come from either this option or that option. And then story done. Shear capacity is calculated. This figure just helping us to let you imagine what we mean with buckling failure. And I think just to let you know, this is just a practical thing. Sometimes you have a beam which is working very well in bending, working with deflection, we're going to talk about next, and it's really good. But there was a very strong column somewhere at the near the support. Say this is the supporting column, and there was a column coming from a level above. Maybe it's carrying heavy loads, 2 stories or whatever. Usually the bending here will be okay. The deflection will be okay because we're not putting the column in the middle of the span, right? But the problem, we're shearing it a lot here. So instead of going, if it did not work based on these formulas, instead of going and upsizing the beam to a bigger section, what we can do, we can simply just weld, just weld the two stiffeners on the side. So that means, because usually if it's gonna fail, it's gonna first fail by buckling. So the solution, instead of going and getting a bigger beam, which costs maybe another 3,000, if we're talking about, say, 10 beams you need in a project, and that may cost you 10 to 15,000 maybe to beef it up to another section, then just simply keep the section as it is and weld those plates, so you end up with this capacity, better capacity. Okay, because remember here it's same, this one, it's same on here, but we still gonna multiply it down by another factor. So you always need to employ these practical measures when you make decisions. So that was about what? That was about shear. It's really very friendly topic, straightforward, and you're gonna also, that authentic beam we ask you to work on, the LMS will take you through the story as well, how you're gonna do it, and you're gonna practice this tomorrow. Tomorrow you're gonna practice this tomorrow during the workshop. Last topic we have today, which is again simple, serviceability. Serviceability, right? Now, in SD2, which you all passed and got your perfect marks there, SD2, we took you through the concepts and the theories that showed you how to find or calculate the deflection in function of the loading, the span, the I value, the E value of the material you're using. Again, we showed, or you've been studying and you've been assessed, or you know about it, you should tell me how it works. If you got a simply supported beam with uniform loading like this, then there is a formula that can tell us what's the maximum deflection for that beam, and these are one of the formulas we use. If we got a cantilever, which we don't have here because you can find it in many textbooks. If you had a cantilever, you can have another formula. If you have a point load, not uniform load, you will have another formula. So what I'm trying to say, this formula is basically what you need to use, full stop. So if you have a simply supported beam taking a uniform load like this and spanning this much, power it to 4, E is, what was E? 200,000 for steel, MPa. Yeah, which we talked about, and you're gonna know that. I, it's the IXX or IYY value, which you're gonna get from one steel book tables, which we're gonna let you use more this week. So you just need to know which formula to use from literature, or from textbooks you used, or from lecture notes you used, and then you need to apply them. And then you're gonna find from this formula, you're gonna find your actual deflection, say it's 12 millimeters. But you have to make sure this 12 millimeters, is acceptable. You have to then compare it with the standard. We have a standard, which really gonna tell us what's acceptable, what's not, which is here. So if you remember 1170, I said to you 1170.0 is the general standard for structural designs, and this standard got a table, C1, which can guide engineers to check the maximum deflection. For example, if we have a floor beam, you're talking about floor, they said if you are worried about sagging of the beam, make sure mid-span deflection does not go beyond. If let's say we are under this case, that does not go beyond span over 500. So then what I will do, I go back to my notes, which is here. Yeah, so as I said, I've calculated 12 mil. Then what was the span of your beam? Say it was 10 meters. Then you divide 10,000 millimeters over 500. Right? So this will give me, this is a lot. I don't think it's acceptable anyway. So 10 meters deflection, it will allow, just to let you know, now if you read carefully the table, someone will say, so I'm allowed to go to 50 mil. Remember here, as a practicing engineer, you need to know if there are tiles or whatever. There are other limitations where sometimes we document these answers to the architects because nowadays they got very special finishes and materials. The rule of thumb is we typically maximum deflection we would allow in a residential floor 25 millimeters. And some properties we go up to 12 mil if they're going to use a lot of tiles there, right? So that standard, yes, it will give us a general figures. However, you always need to make sure what materials in your test or exams, you will be given the ratio or you're going to be asked to use specifically which materials to work with. Okay, and you just need to apply whatever cases you have here. All right, so actually it was 20 mil. I think I made a mistake there anyway. I was over 500. It was actually 20 mil, which looks fine, but still looks a lot. So this is going to give me 20 millimeters, right? This will give me 20, not 50. 20 millimeters, which looks fine, but still for some residential, especially when you have timber and on the timber they put tiles. I know people that like in the bathrooms or whatever, you need to have tiles. You would typically worry about 20 mil because they may crack the tiles on a timber house. But this is just for your information in your test or exam. Just if the formula gave you 20, use 20. It's really all good. So that was the story really behind deflection. Deflectioner shield is really simple. Usually students cruise through them very easily. No issues, no complications. But pay careful attention to the bending, the MB and MS. Make sure you know how we treat them, what's the difference, how we work with them, and you should be good. I've got very quick notes here to talk about the design. Now by this, we are done actually with beam design. So in week 7, you will have very simple topic as well. As I remember last time I said to you, the subject will start getting a bit easier for you. That's what we see with students typically, but you just need to keep working. So some of economical notes which we always like to share, I'll say them quickly. So always aim for economical designs. In terms of resisting moment, avoid non-compact sections. And that was a skill you learned last week when we told you how to find ZE, which depends on whether it's compact, non-compact, or cylinder. So we're saying avoid non-compact section and also cylinder section because this was the best. Now, yeah, because usually you will not worry a lot about laterally restraining the beam. Okay, and then you can typically rely on MS, which will give us the best capacity. So, and I think that second one is talking about also avoiding cylinder beams without, because you're going to save up. So these are just general things when you think about designing beams. Now, in terms of shear, I think I talked to you about this. And instead of, if the beam didn't work for shear, and instead of upsizing the whole beam, go put some stiffeners at the sides, and that will cost the supplier nothing to really just weld the plates on site. They do this on site while they're constructing it. With deflection, if it didn't work, again, don't upside the beam. Think about having a spot within your floor, like maybe you have a wall under, and try to stick a column there to cut the span. So if we got like a 10-meter span beam, and we're trying to span the beam from external wall to external wall, which you find is deflecting a lot, then yes, it's a problem. But try to see, maybe you got, a small bathroom or living room and it's got timber stud, and try to stick a steel column here to actually cut the span and take it from 10 to 7 or 6. That will help a lot with the deflection. That's really what we mean with cutting the span, reducing the span somehow as applicable. I know nowadays people are trying to design their houses or any apartments with open spaces, but there's always possible ways. I think the last points here, use these sections, universal beam, universal columns. You're going to know more about this from the one steel tables. They widely used. Avoid and use standard connection details as possible, just to avoid mistakes. If you keep making special connection at each point, it will cause mistakes and issues. Yeah, keep things simple. Keep things simple, which that's where people will like your design. Don't overkill it, overcomplicate it to get things. Yeah, always think about buildability. Buildability is one of the key success in you have to know how things are built, because typically architects or many other people may not think about this part of the process. All right, so I think these are the notes I wanted to share with you, and I think we have one walked example to go through there. Thank you, Vipul.
Thank you, Heather. Now here we have checked the adequacy of the fluxural strength of 460 UB. So adequacy meaning the bending moment diagram is given to you. So design. So adequacy meaning that let me write it here. Design bending moment that you can extract it from the bending moment diagram is 106.4 kilonewton per meter. So adequacy, that beam is 460 UB, 67.1. So that is this beam. Now this loading they need to carry. So the capacity, either the member capacity or the section capacity, either of these should be greater than M star. Then we said beam is adequate. That's what they want you to check. That's simple condition. Which one we going to calculate? Either MB or MBs. I will tell you that one. So that's the adequacy. Bend in the strong axis. Strong axis meaning that if you have a beam, this is would be X axis. So that would be your strong axis, and that would be your weak axis or minor axis. All loads are applied to the top flange of the beam. Top flange of the beam meaning that if you have this beam, this I beam, this is the top flange, this is the web and bottom flange. So all the loadings are applying onto the top flange. The beam is partially restrained at the end. So if I look at here, this is partial restraint P at A, partial restraint here. Where lateral deflection are effectively prevented. So there is no lateral restraint. Lateral restraint meaning that if you have a beam, I hold it beam in a way that this beam will not laterally restrain. Lateral restraint means this is a long axis, it will not come out. You can see when I load it, it will not laterally restrain, right? This is longitudinal restraint, this is lateral, the small side lateral. So this point will not come out. This point will not do it. This will be stored. I hold it like this so tightly on the both hands. So these points are stay as it is, not laterally restrained. So laterally prevented, and twist rotation are pastorally surface. So twist may happen. The restraint is available only at the end. So as you can see, restraints are only available at the end. There is no restraint in the middle. As you can see in the figure as well, the restraints only available in the this one. Load P dash is due to the dead load and live load. So they already calculate this P star equal to 1.2 G plus 1.5 Q. We don't need to do it. This is factor load already. So they given to you, and it's apply on the top flange of the beam, and they give you W star dead load only is 0.65, and they have given you this bending moment diagram. Now these notes I will talk you through later. Now for these examples, we always make this check on close 5.3.2.4 segment with full and partial restraint. There are a couple of things we are not worried too much about those because they are from segment with an equal flange channels. We don't worry about channels and so we just mostly talk about these I section. So this first equation. Now what is this first equations? Now the first equations tell me that if your length from this point to this point over radius or gyrations is less than this one, then your beam will not be laterally deflect. The lateral torsional buckling, the fluxural torsional buckling will not occur. Will not occur meaning that when you see the header shows the video, the first video that it will yielded, it will not going to come out like this. It will not going to this portion. This one is not going to like if I show it to you in a diagram way, that if you have a L over Ry less than 80 plus 50 beta m, very important equations by the way, and very magical, very powerful, whatever you say, Fy. So when this happens, let's say this is your beam. I hope you can imagine this beam. So when this L from this point to this point, L and Rustain here, then if this is true, if this one is correct, then you will not have this Rustain. But if this happens, L over Ry 80 plus 50 beta m square root 250 on Fy, meaning that your length is little bit bigger. Little bit bigger is significantly bigger. Let me draw it up carefully. So this length that we draw it, same beam by the way, but this length is little bit more. Little bit more meaning there is more, significantly more. So you have this length now from this point to this point, lateral resistance L. So then what gonna happens? This guy will do this. This guy will just going to kick out from his original positions. I can imagine, you can imagine that, right? That it will just going to do this way. So this is called fluxural torsional buckling, and this will also twist. This will stay here, and this will twist as well. So in that case, if these equations happens, then it will govern by member moment capacity. We need to find member moment capacity. This is member moment capacity. And if these things happen, this condition, then you have section moment capacity. You don't need to calculate the member moment capacity. Right, so I hope it is clear. So first we need to calculate which, need to decide which one we need to go, MS or MB. So that's where we need to find this one. Left hand side is L over Ry. What is our L? Our L is 800. Sorry, 8,000. So let's put that 8,000. You have 8,000 millimeter over Ry. What is the section, by the way? The section is 460 UB 67.1. So let's find the Ry. Probably it's a good idea to show you on this. What can I say, on the screen, so you can find more clear way. Otherwise, you can't see the stuff that we want to show you. So let's open it on the screen rather than on this one. Okay, so let's. So we have. I think it's not working properly. So. Yep, that is working now. Now, we have 460 UB67. 460 UB67. That's, you can see. And for that case, this line here, Ry is here 41.2, as you can see from one still tables. So 41.2 millimeters. If you use the calculators, you will get 194. Right hand side is equal to 80 plus 50 beta m square root 250 over Fy. So 80 plus 50 beta m is a moment ratio. If you just turn the page over a little bit here, you will find the three options. You can take beta m equal to -1. Don't take -1 straight away. It would be very conservative and very uneconomical. if you are smart engineers, you will go for these two options, which is minus 0.8 for segment with a transverse loading. Transverse loading meaning that this is your transverse loading, that you have this UDL load, that is your transverse loading. Yeah, so we have transverse loading, so we can take minus 0.8. The ratio of smaller to the then your beta m would be 0 because this one. So let's go for this option, minus 0.8. So you have minus 0.8 times 250 Fy. You can again take it from the one sheet table. If you move the one page over, you have 460 UB 67.1. You have this 300 or 322. I think from this one, your flange is 300. What does it? Flange is 300, wave is 320. So flange is 300, wave is 320. So generally we take is the smaller value, conservative 320. Sorry, 300. We're going to take it in that case. So if you have a choice between selecting materials between these two, you select the small one. So 300 and you get 30. So you can see left hand side, which is L over Ry, which is 194, is greater than your 80 plus 50 beta m square root 250 Fy, which is value of 30. So these equations that we have is not true, meaning your functional torsional buckling will occur, meaning you don't have enough length. You look at the size, 8 meters, and you don't have anything in 8 meters. So of course, this guy is gonna bang, come out, right? It will come out to you or it will goes back, right? There is no one to hold it, right? So if I take the piece of paper, let me take the piece of paper here. Let me take the piece of papers. If no one's holding it and if someone applying it, they will do this, right? They will do this, but someone holding it in the middle and something, then it's very difficult for it to come out, right? So if it is too long, then this condition L over Ry is greater than. So this is a lateral torsal buckling. If it does like this, if you are showing this one, so this is straight beam, and someone load it, this one is happened like this. So lateral torsal buckling occurred. In that case, we can't calculate MS last week. So here we need to calculate MB, which is a member moment capacity. So that's fine. Let's get the equation for member moment capacity. So if you come back here you go. You have a open section with equal flange, segment of constant cross sections, close 5.6.1.1. You have this member moment capacity MB, alpha M, alpha S, MS less than or equal to MS. Well, alpha M is moment modification factors. Alpha S is slender reduction factors, and this is nominal section moment capacity. So let's write it down, these equations. Member moment capacity. So we have a member moment capacity because why? Because L over Ry is greater than 80 plus 50 beta m square root 250 on Fy, right? If this one L over Ry, L over Ry is less than, then we just calculate the section moment capacity. Let's put this section moment capacity, meaning that fractional torsal buckling will not occur. So that's all good. We always make this check, by the way. Without these checks, we don't know. Right? So let's calculate member moment capacity. MB is equal to alpha M, alpha S, and MS. So let's work it out, and that should be less than or equal to MS. We're going to make this check. Now let's work out the one by one. Let's get alpha M. Alpha M, what is this called? Is called moment modification factor. Now, what is moment modification factors? Is it our friend or is a penalty to our design? It is our friend. It is our friend, meaning it is helpful. It is helpful meaning it will save your money. Save your money meaning you can use the smaller cross sections. Alpha I'm going to help you. Alpha I'm going to help you in a design, but standards will going to put some limitations if you have a friend. You can't take a lot of help. So it is moment modification factors, as I said, name written here. There are a couple of options to get the moment modification factors. Moment modifier shall be taken as one of the following. You can take one, which I don't recommend you to do. I will tell you when you can take one. Value obtained from table 5.6.1. Okay, where is it? Here you go, table 5.6.1. You can use these tables. How you can use these tables? You can look at your loading diagrams, your load diagram. Then you look at your bending moment diagram. You compare approximately. Now look at the restraint, where the restraints are. That's the first things that you need to look at, where your restraints are. That's the first thing. Look at the bending moment diagram for rough comparisons. You have a bending moment diagram within the restraint. So look at that bending moment diagram for rough comparison. And look for closest fits. Just need to look closest fits. This is not an exact matters, by the way. You will not going to find 100% person's close fit. So this is approximate. This one is like a simply supported and so on. This one here, 5.6.2 is a cantilevers. As you can see, this is fixed, and this end is free. There is nothing here. So if you have cantilevers, you can like a balcony, you can come back here to calculate alpha m. Very simple here. If you have like a simply supported and within the segments, you can use this table. So I hope you understand between 5.6.1 and 5.6.2, how, when and where you're going to use it. There are different cases. We may experience some of those cases as we go in workshop and different examples as well. Now for our case, there is a third options that alpha m can be calculated using the moments. One condition though that you need to take it 2.5. Now I put a note, this equation account for non-uniform moments. So when you look at the alpha m equal to 1, alpha m equal to 1, this is very bad. If you have a moment like this, is 1. You have no chance. This is the worst moment that you will experience in your structures. If you have this constant moment, you will have this one. When you're going to get this kind of constant moments? If I load the beam, let me put this one. If I load the beam, let's say P1 some load and P2 some load, same load. Let's say P1 is equal to 10 kilonewton and 10 kilonewton here. Then my bending moment diagram is like this. Look at this region. These guys here will going to experience heavy moment here, constant moment. Your alpha m equal to 1 here. You can look at that, right? Because this is the worst case scenario in the moments. So when the buckling happens, this guy is gonna come out. If I draw this one, this guy will have this, but this guy heavily come out. Right? Look at these guys here. They will kick off significantly because of these constant moments. So therefore, standards knows that this alpha m value 1. By the way, alpha m cannot be less than 1. You can take 1 or more than 1. So if someone in the test and something, they put alpha m equal to 0.5, no, you will have 1 or more than 1. The starting point is 1, and then it goes up to 2.5. You can't go more than 2.5 or 2.25 or something. Yeah, 2.5. So you have alpha m value starting from 1, finish at 2.5. Don't go over 2.5. Don't go less than 1. So I hope it is makes sense. These tables. Anything else? I think full or partial restraint. That's cross meaning. And there are beta m. That's I already mentioned how to calculate that. So this is all good. Not really. So I think we have this. Oh, I need to explain you what is this non-uniform moment. Now this guy is telling me that, okay, if you are designing this whole beam in the red has a very small moment in this region. You can look at this. This guy is experiencing very small moments. This guy is experiencing very small moment, but this green part is experiencing heavy. So the standard said the alpha m equal to 1 here. That's okay. But in this zone, you might have alpha m equal to 1.65. and alpha m equal to 1.65. So look at that. There's this non-uniformity in the moments. So in that case, they said, okay, you don't need to take alpha m equal to 1. You can take alpha m equal to 1.5 or something. That will allow you to just work the whole beam together in the some zone low moment, some zone high moment, some zone low moment. And then standard said, okay, I will tell you to have this one converted like this, like your uniform moments, right? So that's what the alpha m is. Alpha m. So here we can use this equation alpha m equal to. By the way, there is a typo here. Alpha m equal to. Just there is a typo in the standards maybe. So alpha m equal to. Let me put 1.7 mm star over square root m2 star square plus m3 star square plus m4 star square. Okay, I just copy this equation from here. Mm is the maximum design bending moment at the segment. That's useful information. M2 and M4 design bending moment at quarter point of the segment. That's also good. I will explain you. M3 design bending moment at the midpoint of the segment. So let me explain you that. So it says that maximum moment, quarter points, and midpoints. So if I come back here in our diagrams, so this is 2000s, 2000s, and one more 2000 and 2000s, and this is 54.8. Now this is maximum moment. You can see m star. This is a quarter point, m2 star. This is your quarter point, m4 star. And this is your midpoint, again mm star, and the midpoint is m3 star. Right? That's all good. So m2 54, m4 54, mm1 to 6.4, m3 is 106.4. So that's good. Equal to 1.7 times mm, 106.4 kilonewton meters over square root m2 54.8 square plus 106.4 square plus 54.8 square. You get 1.37, which is less than 2.5. Therefore, it is okay. Less than 2.5, which is okay. Now I can show it to you from the table as well. Tables here. I'm not sure which one we can pick. Let me go back to the figure again. Go back to the figure again, meaning that we have this kind of a loading restraint at. So we have something like this. We have something like this restraint, and then we have these loadings, which is 50 kilonewtons. There is a uniformly distributed load, and then you have bending moment diagrams look like this, right? So if I just keep in mind these figures, okay, you have a UDL load, but that's okay. 50 is the more one. This one does not match. This one does not match. This one looks closest match because you have F, and if I take A equal to 0, is F will comes in the closer. You have UDL load, but you don't have point load. Yeah, so I think the closest match and the bending moment diagrams, the close one match is this one. Do you agree with me? We don't have this bending moment, this. No, I think this is the closest match I can find, the bending moment diagram. Look at the diagram again. Look at the diagram again, bending moment diagram here. So you happy with me that we can go for this one, where I can take A equal to 0, that it will comes in the center because our load is in the center. So if I plug A equal to 0, I will get 1.35. Do you agree with me? That A, if I substitute this, this A equal to 0, I would get 1.35. So if I get this 1.35, let me check with the equations that it makes sense or not. So from the table, alpha m equal to 1.35, which is close, as I mentioned in my notes, that look at for the closest fit, no exact methods. So this is not exact methods. You have kind of a partial things. So 1.35 still okay. We can adopt either 1.35 or 1.37. So I show you how to use the table as well. This is coming from tables, and this is the exact value from our equation. So alpha m. Now, then the alpha m we find 1.37. So we done alpha m. What is alpha s? Let's go and find it. What is the name of alpha s? Let's go and find it. The alpha s is slenderness reduction factors. Slenderness reduction factors. Okay, so let's write it down. Slenderness reduction factors, and this is not our friend, because that will reduce our moment. There is a penalty for that, not have enough restraint. Now, how do we calculate alpha s? Alpha s, yeah, there is a typo again. Put the s here. 0.6 square root ms over mo square plus 3. Please note this 3 is within the square root. When you do the calculators, don't forget that this 3 is outside of the square root. I can lift up here. Please note this 3 is within the square root. And this, do not forget to multiply 0.6. This 0.6 sitting outside. There is a common mistake that students are just falling into this trap, that 0.6 they keep forgetting. 3 they put it square root in the calculator. So have some practice to use this equation. So alpha s 0.6 there. Put it in this one, and ms over moa square plus 3. This is within the square root, by the way, and ms on moa. This is the alpha s value. Okay, now in these ones we don't know ms, so let's calculate ms. What is ms? Ms is a nominal section moment capacity. How do we get the nominal section moment capacity? There you go. Nominal section moment capacity, ms, close 5.2.1 fy times ze. So ms is equal to fy times ze. Now ze value, you can check compact, non-compact. You remember last week, and you can use ze here, or ze here. That is a long process, half an hour process. I don't want to go through this long process. If any examples that you said, okay, perform the compact, non-compact, and slender check, then you perform it. But for you in this slender one, I encourage you to use straight away these guys. Here they already give you the z value 400. So this is first bit where you have get the geometry, all these geometric dimension. Next page, if you come, it has a material property. So 406 UB 67.2. This straight away give you this z value 1480. Do not forget to multiply 10 to the power 3. And we need to take it about the x-axis. We don't want to go for y-axis, that is the weak axis. So look at this. This is weak axis 230 only. We don't want to go for that one. So we just go 1480. So Fy 300 megapascals, which is Newton per millimeter square. Zd value is 1480 times 10 raised to 3 millimeter cube. So we straight away the one still table already use these equations. These three equations, and they already given to you. So they did perform the calculations for you. So they straight away manufacturing supplier already given to you. So if you just calculate this, you will get, let's say 300 times 1480 times 1000. You get 444,000,000 Newton millimeters. So 444 kilonewton meters, right? So MS is done, nominal section capacity. Now MOA. What is MOA? What is the name of MOA? If you go back to the standard again, couple of pages, MOA shall be taken either MOA equal to M1, reference buckling moment, or value determining from the elastic buckling. So we don't worry about this B part. We don't want to do the elastic buckling analysis. So we just take a reference moment, reference buckling moment, and that is MO. So that's the big equations given here, and I will go through it step by step with you. So MO equal to MO, and that is called reference buckling moment. Now, how do we get the reference buckling moment, MO? Look, guys, this one is not our friend. Our not friend means there are big numbers. You will going to create a lot of troubles in the calculators. I will put the stop sign. You remember my stop signs in SD1. We put the stop signs, and it helps. I see some students are using my stop sign in the assignment in the final. It helped them. It helped them to spend. So I don't want to just rush and then we don't know where we're going. Right? We will put stop sign, making sure we are progressing in a correct directions. Yeah, some student might say, still you make mistakes. Yeah, I know you can still make mistakes, but this stop sign gonna help you at some extent. So we have pi square E IY L square GJ plus pi square E IW L square. No, these reference buckling moments are controlled by three parameters. That buckling of the beam, you know this Euler's buckling, like it will buckle, right? So it's pi square E over L square. You remember this Euler buckling formula. That is the buckling of beam. Twisting of the beam, GJ, like elastic modulus, that is the shear modulus, and J. I think I will tell you what is J as well. J is a section constant. Right? You can see here J, and this is the wrapping constant. They will wrap. So that's wrapping pi square E, wrapping moment of inertia over effective length. So this is the big equations. I will tell you one by one. Pi square, Young modulus of the steel, 200,000. I think you don't need to remember, but probably they have given at the front that you can take E equal to 200,000 if it is given. Yep, Young modulus of the steels, and it is 200,000. Somewhere they might have they have written. I will find it out if you don't want to remember somewhere. But I know this is all 300. Even in the one steel tables, they mention this is 200,000 megapascal. So this IY, you can take it from the one steel tables. Let's go and get it. I don't want to write this big equation at the moment. We're going to write it. So 460 UB, IY is here. IY is here. And this is 14.5 times 10 to the power 6. So that's good. Let me write IY 14.5 times 10 to the power 6 millimeter power 4, which is moment of inertia about the y-axis. So IY found. That's all good. IY is good. Effective lengths. Effective lengths has a story. That is here. Effective lengths close 5.6.3 KT, KL, KR, and L. So let's write it down. There are three Ks. Effective length equal to KT, KL, KR, and small l. Right? So there are three Ks. Let's break the three Ks one by one. So these are twist restraint factors, load height factors, and lateral rotation restraint factors given in table 5.6.3a, 5.6.3b, and 5.6.3c. Come back here on this one. Look, these tables is not so much friendly. I have some notes. I will crack it those one by one. So let's first find the twist rotation factor KT. So let's find the twist rotation factors. KT first is the twist rotation factor. Now, in the twist rotation factors, you need to look at the restraint arrangement. You need to look at the restraint management. AF stand for Let me go back and take you somewhere, meaning to identify what is F. So if you turn the couple of page over, and you will see fully restrained. Clause 5.4.2.1 is stand for F. FF meaning if you have two ends, you know the segment has two ends. F here, F here. So that is FF, fully restrained. F, one end is fully restrained, and L meaning laterally restrained. L is laterally restrained. They have given you figures, but I will explain you what is that one by one. So FL, LL laterally restrained, F fully restrained. U means that is no any restraint, is free. P means partially restrained, as you can see, partially restrained. And that's it. There is nothing else. Yep, there is nothing else. Now, how are you going to identify this, whether it's fixed or whether it's laterally restrained or whether it's U or whether it's P? Because there are four things: F, L, U, and P. U is simple. There is no restraint, and then this good. So you still have three questions. How do we know F? How do we know L? Or how do we know U? So let me help you with that one. That in that case, we have some. Okay, let me help you with that. Some figures are there. But for our examples, I think it's given already that beam is partially restrained. So it is P at the both end. So we already know it is PP. But I want to give you the full pictures. Because look at this. I think this is in our Bendigo. If you go to Eagle Hawk badminton, there is a stadium badminton, Eagle Hawk in Bendigo. When I go there, when I see the structures, it's just remind me of wind loading and steel. So I take a pictures from the mobile and just help me to explain. So look at this beam that we want to. Let me use some different colors. Look at the beam, this one, right? So you can see this beam that I put it in the green. So this beam has these purlins. You can see these purlins on the roofs. Yeah. So that kind of one kind of a restraint, that you might have a partial restraint here, partial restraint here. You might have P here. Look at this fly bracing. Look at this end. You can see, right? So you have a purlin plus this fly bracing. See, these guys will not going to move. These guys not going to move. It could be considered as a fix, right? Again, this one P, this one P, this one fix, as you can see here, right? So that's typical how it's going to get the restraint in one of these one. This is just an example for you to just experience. Now, for our case, there are various things. Various things meaning I need to give you the critical flange concept as well. So there is another word that they put here. Look at the C. What is C? Because look at that, everywhere they put C and C. So what is that C? C is a critical flange. What is critical flange? Critical flange is a flange that deflect further during the buckling. So you have two flange. Look at this. You have two flange, top flange and bottom flange. How do we know which one is a critical flange? So when it's loaded and one flange would be stay in that positions. It will not come out laterally. So but one, you need to compare both. That another, the top one, if I load it, simply supported, this top one will come out, this bottom one will stay, because that is the compression flange, and compression will cause the more buckling. Tension will not gonna cause the buckling. So this will consider as a critical flange, because so you need to check which flange going to buckle more, which going to laterally deflect more. That is a critical flange compared to the another one. So you can look at that. Look at in these guys, this flange, if I look at like this, if I have this one, if I fix this end and if I load it, this guy will come out. So this is critical flange. This will stay. It will also deform, but this not like this one. So this is critical flange. So that is the concept of critical flange. Now all these figures are given here to say if it is fully restrained, you will have this kind of a concept. If it is partially restrained, your critical flange will have this concept. If you have a rotationally restrained, you have this concept. If you have laterally restrained, you have this kind of concept. But in our book, there is a very good figures given to you. Very good figure given to you, meaning that, okay, let me fix this. So look at this one. This is, by the way, I taken from this book. You remember that in the start we have given you these books, right? It is available online, and you can go through that books if you think where this figure coming from. Okay, that is also given in the standards, all the figures. So if you look at the partial restraint of the beam, partial restraint meaning this one. Partial restraint like these figures, this is flexible fly bracing and these kind of examples, but here they are more clear. Look at this fly bracing here, and your critical flange is not fully welded here, critical flange is not. So this is the example for partial restraints. You have a slab here, your critical flange is free. You have this these go this way, this is a critical flange, and also there are examples. If you want to have a lateral restraint for the beam, if you have critical flange and someone jointing here is a partial restraint. Someone, your critical flange, someone with the welding on that one is a laterally restrained beam. Lateral rotation restraints, you can see these rotations are not allowed here. So these guys cannot rotate, right? These guys cannot rotate. You can see they are fixed. This figure is very helpful. This is a, by the way, top view. This is a top view, meaning that if I have a beam, someone watching from here, so they draw these guys here, they draw these guys here. So here, fully F or P, fully or partial. This is free, right? So this is all the figures that you can see. You can experience this, but I think in the, so I hope it is makes sense how to do this FFPP. It's about how you get a connection. So we, in our case, it is given PP. So I can say 1 plus 2 D1 on L TF 2 TW over 3 NW. Let me write it down for you. AT is 1 plus, because we have TT, PP, sorry, 1 plus 2 DL on L TF on 2 TW 3 over NW. So what happens here? NW, sometimes, you know, you might have a beam which has a 2 waves. Okay, this is the wave number 1, NW equal to 2 here, because 1 here and 2 here. So but in our case, NW equal to 1 because we have only one flange. Now in the figures, let me explain you this KT, that if you have no partial restraints, then you can take 1. If you have one partial restraints, 1, and look at that, 1 P, then you can use this one. If you have 2 partial restraints, 2 and partial restraints. So if you have a no partial restraints, there is no partial restraints, then you take first 1. If you have only one partial restraint, let's say 1 and is partial, another one is fixed, then you have used this one. And if you have 2 partial restraints, you use. So that is just a wording that I just elaborate more. So in this equation, 1 plus 2. This is not DL, it is D1, by the way. And D1, you can take it from our 650. D1 is here, 428. D1 is, by the way, this. If I draw it up, this is your D1, 428. So 428 over length L. I think the length L you're going to get it is your 8,000. That is your, yep, 8,000 given in our examples. And TF, thickness of the flange. Thickness of the flange, 12.7. 12.7 over 2 TW, thickness of the web. Thickness of the web, 8.5. 8.5 and cube over 1. So if you do KT by using the calculators, you get 1.05, which is good. Now, KL. KL just down below, load height factor, KL for gravity load. You have within the segments or at the segment end. We are looking for a, so these are cantilevers. You can see these two is cantilevers, two is cantilevers. If you have a, so we don't have cantilevers, so we can't use two. We have top flange loading. So you can use 1.4 or 1, and we have partial restraint. And this is within the segments. Look at the figures here within the segment. So you have these restraints and you have loading between the two. So you have within the segments and you have PP. So we can have 1.4. And in the question it says that load was on the top flange. So it's 1.4. KL 1.4. KR. KR is here, lateral rotation restraints. Again, first one is cantilever, second one is simply supported, third one is end span, and fourth one is middle span for of fixed fix. So we have a partial restraint, by the way. So, and we don't need to have any rotation restraints. We don't have any rotational restraint. So we have none, and we have simply supported as well. So 1. So that's, let's take it 1. So if I know all these values, I can plug it here. 1.05, KL is 1, KR is 1, L is 8,000. I would get 11. Oh, sorry, this is 1.4. We got 80, KL 1.4, right? Yep, KL 1.4 and KR equal to 1. So you get 11,760 millimeters. So we find LE, I think in these equations. In these equations, we find LE, we found IY, GJ. Let's get the GJ. So G, if you come back here, where is the G? Where is G here? Shear modulus of elasticity, and it is 80,000. Okay, and that is given probably in the one still probably in the workshop. If I get the time, I will show it to you that this is constant value and it should be 80,000. So G equal to 80,000 megapascals. J J value is probably given in our J. Here you go, 378 times 10 to the power 3. So that is given in our one still table. 378 times 10 to the power 3 megapascals. So I have J, E 200,000, IW. You can get it from the one still tables. IW wrapping constant 708 times 10 to the power 3. 10 to the power 9. Yep, 10 to the power 9. So IW equal to 708 times 10 to the power 9 millimeter power 4. So if I have all the values now. I have pi 200,000, IY get it from one still table, LE I calculated, G 80,000, J we get it from the one still table, pi square 200,000, IW we get it from the one still table, and LE. So if I plug all the values, I would get M0 equal to 91.3 kilonewton per meters. I want to put the stop sign because look at this. This is a very mistake attractive or error attractive equations. So I want to put a sign. So for length between 5 to 10 meters, your M, if you get M very large, let's say 1000 kilonewton per meter, kilonewton meter, it is a suspected value. You should not get more than 1000. Look at the numbers, 90, 100, 200, 300 is okay. But somehow if you put this, because 10 to the power 9, 10 to the power 6, 10 to the power 3, if you miss a one single zero in square root and all, ooh, you will have disasters. Put a stop sign here. Look at the M0 value. That should be within this 1000 kilonewton. One. All right. So you got everything now. So we can calculate alpha S. Alpha S equal to 0.6 square root. I'm just by looking at this one. MS we calculated, MO we calculated. So I just plug this value. MS, we calculated 444. Where did I calculate it? MS? Here you go, 444 kilonewtons. 44 kilonewton meters over 91.3 kilonewton meters. MO square plus 3 plus 3 minus 444 kilonewton meters over 91.3 kilonewton meters. Right. So if you multiply that, you get 0.18. Now there is a quick check that you can make. Alpha M times alpha S is alpha M. How much we calculated? I think alpha M 1.37 we calculated. Yep, 1.37. So 1.37. We don't need to make these checks because there is not given in the standards. Let's calculate MB. MB equal to alpha M, alpha S. We will indirectly make these checks. Alpha M, you get 1.37, alpha S 0.18, MS 4440 kilonewtons. So it will give you 109 kilonewton meters, which we need to make a check. Check meaning it should be less than or equal to MS. So should be less than or equal to MS, which is 4444 kilonewtons. So that is okay. That's indirectly checked that is less than 1. Now, then we just multiply by capacity factors. 5 MB equal to 0.9. Someone might say where this 0.9 coming from? I can show it to you. 109 kilonewtons, then 98.5 kilonewton meters. Meaning where this 0.9 coming from? If you come back to here. Here you go, table 3.4, member subject to a bending. All this one, all are 0.9, right? So we take 0.9 there. 5 MB. So let's check. 5 MB, which is 98.5 kilonewton meters. Let's compare with this M star. M star value from the bending moment diagram is 106.4. So this is 106.4 kilonewton meters, which is less than. Therefore, beam is not adequate. Right? It's not adequate, meaning it does not have enough capacity. 98.5. Look at that. But we have 400. Look at this 44440. 98.5 is not. So if someone said, how do I make these checks? So if you want, you remember that we have an examples. So we have this loading. And this is 50. So this is a restraint here. So if you want to make this beam working L over Ry, you can just calculate 80 plus 50. What is the 80 plus 50 right hand side? I can quickly do it for you as well. So there was 30, by the way, and Ry is 41.2. So Ry was 41.2 and this one was 30. So if I put the restraint 41.2 times 30, let me use the calculator. 41.2 times 30, you have 1236 millimeters. So if you have 8000 millimeters, if you put the restraint at 1236 millimeters, you might have a capacity. Or another option is to just go higher beam, the larger beam, meaning you have 467, you might go 530, 82 and do the iterative process. Yeah, but that is not part of. They just wants to check whether it's adequate or not. It's not adequate. So you have an option to put more bracings to stop buckling. So it will increase the capacity because we get a huge penalty. Huge penalty meaning, look at this penalty. Where is the penalty? Ooh, look at this alpha S. About 0.18, take away 1. About 82% penalty received from here. Look at that, 82% penalty, 82% is gone. We have a capacity about 44440, but because this lateral torsional buckling occur, the standard put the heavy penalty on our design. But this guy is helping us by some extent, but these guys 0.18 is quite low. We need to keep it close to 1. That's what we want to do. If you put the bracings, these alpha S will increase.